We're going to be talking a little bit about linear functions and polynomial functions in this video. This is a very brief review, just to make sure we're all kind of working on the same page. So linear functions are often written in slope-intercept form. It's probably one of those formulas that you remember more than any other. And m, of course, is the slope of the line, and 0b is the y-intercept, hence why it's called slope-intercept form. Some characteristics of linear functions: they have a constant rate of change, and that's what the slope is. It's measuring the change, and it's a number. It doesn't itself change. So what does that really mean? It means for every change you do in x, you're going to get the same amount of change in y. Or the increase or decrease in output is always going to be the same. It isn't going to start increasing more swiftly or decreasing more swiftly as x values change. So you can kind of think about how you want to describe that to yourself and fill in that section there. But what happens when you graph a linear function? What does it look like? The graphs are lines. Now, it's really important to just note we do have one kind of line that is not, in fact, a function, and that would be vertical lines. Vertical lines have no slope. They're not functions. They do not pass the vertical line test, etc. So when we talk about linear functions, we are not talking about vertical lines. What about domain? What kinds of numbers can you plug into a linear function? Are there any kinds of restrictions? And you can put any number you want into x here. And so the range would be negative infinity to infinity. Some people will write that as the all real numbers. That's what that symbol stands for here. What about the range? What kinds of numbers are you going to get out? If you're graphing a line, in general, you're going to have all possible y values. So again, the range of most of these is going to be negative infinity to infinity, but there is one exception to that rule. There is one kind of linear function that does not have this range, and that would be the horizontal line. Their range is only one number. I'm going to use the pound symbol or the hashtag to stand for the word number because it's a lot shorter to write. Okay, so if I have just a standard line that has a slope that's not 0, then I will hit all of the y values in my range. But if I have a horizontal line which has a slope of 0, then I'm only going to have one number, one y value that comes out of that function. And just to be thinking about what kinds of data, what kinds of things actually have a linear relationship in the world. I think one of your most common ones is things like distance equals rate times time, as long as rate is constant. So if you're traveling for 2 hours at 60 miles an hour, then you can calculate your distance doing that calculation, and it would be a linear function. Anything that's along those same lines, like your income, let's not think about taxes, would be something like your pay rate, your hourly wage, times your hours worked. And again, if you were to graph that, as your hours worked goes up, your income would go up in a linear fashion. It would be a line. So those are the kinds of things that you might see. There's more, I'm sure, and you could think of a few. Next, we're going to look at polynomial functions, which are, those things that we can write like this. It's kind of complicated looking when you write it with all the letters. We have coefficients, which we denote with A's, and we have exponents, which we denote with N's. And usually I'm not going to write the whole thing out, so we end up just kind of, and dot 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 means and so on. So what we're basically saying here is that you have a constant and a number times x, and all the way up to the highest power here, where you have some number times x to that power. Okay. So I just mentioned this word. Coefficients. That's what we call all those numbers in front of the x powers. And n itself, that highest number, the highest exponent we have, is called, oh, first of all, it's a positive whole number. It's not a fraction, and it's not negative. And the degree, it's also the degree, which means it's the highest exponent that we see. We also call the coefficient that's on that highest degree term the leading coefficient. So just kind of bringing back some vocabulary for you that you might remember from algebra. So we just talked about these. What are first degree polynomials? It means the highest power that you're going to see is 1. So x to the first is the highest power that you have in a polynomial. That's a linear equation. What about if your highest power that you see is 2, x squared? That's quadratic. And if the highest power you see is 3, then we call it cubic. There are a few other names for the next highest degrees, but we don't use them as often. So just want to go over some details about the graphs of these polynomials to, again, remind you of some of the things you've learned. The reason we're doing this is not because you're expected to graph something like this second graph here, all, just from using these things, these facts, but more to remind you of these things so you have an intuition. If you were to see this graph, you could make some deductions about the equation of the polynomial based on the features of the graph. So you have a sense of what kind of polynomial it might be. If it was an even degree or an odd degree, or if it had a positive leading coefficient or a negative. So that is the point of going through this, is to increase your intuition about these graphs and not make it so that you look at a graph and go, I have no idea what it is, because that's not going to serve you well as you move forward. So let's talk about even degree polynomials first. There are a couple of graph examples here, but when you have an even degree, so it's degree 2, 4, 6, etc., both ends of the graph exhibit the same behavior. What does that mean? The ends of the graph are what happens as you go into very large x values or very small x values. So we kind of are talking about what's happening here or here. And as you can see in both cases, that they're doing the same thing. In other words, the graph is either both going up on both sides or going down on both sides. So what this means is the y values do the same thing when x gets very large and very small. And by very small, we mean negative. So you could We could write negative there if that would be more descriptive. So if the leading coefficient is positive, which is what we have in that first example, then what's happening? Both sides of that graph are going up. So both ends go up. And one way we say that is we could say with that arrow, remember the arrow means approaching. So approaches infinity. They're going up and off to infinity. The difference is if the leading coefficient is negative, as we can see in the second example, then both ends are going down. So they're approaching negative infinity, as you can see here. So the graph of just x to the n, not any other terms. So I'm not talking about something that has like these middle terms. I'm talking more about something that's just x to the second, x to the fourth, x to the sixth, etc. Because remember, we're talking about even degrees here. It has a parabola or parabolic shape. So you can see, you know what x squared looks like. And as you can see in x to the fourth, it has a very similar shape, but it's a little flatter, sort of down by the origin. And that trend will continue. If we drew x to the eighth, it would have the same shape, but it would be even flatter down in this area. So we're just going to describe that here. The higher the degree, the more the shape flattens in the center around the vertex, which is 0, 0. But you'll notice when you add terms, like you did down here, it's not just an x to the fourth. Now I have other terms. You start to get places where the graph switches, goes up, then turns and comes down, then goes back up, etc. And so those are called turning points. Okay. A turning point, which is our question here, okay, is, to answer that question, a point where the graph changes from going up to going down or vice versa. So you can see in this case, I have 1, 2, 3 turning points where the graph literally turns. They're kind of like little mini vertexes in the midst of your graph. So with more terms, the graph will have at most n minus 1 of these turning points. So this is a fourth degree polynomial I have graphed. You'll notice it has 3 turning points, and that's the most it could have. It doesn't have to have any. The first graph was fourth degree, and it really only has that 1 turning point at the vertex. So it shouldn't say it doesn't have to have any, but it certainly doesn't have to have 3. But that's the most it can have. And last but not least, what about domain? In polynomials, the domain is always negative infinity to infinity. You can plug any number into a polynomial, but the range is going to vary. It's going to vary based on what the lowest point is, whether it has a positive or a negative leading coefficient. So it's going up forever or down forever. So we'll just leave it at the range will vary. All right, and we're going to do the same thing for odd degree polynomials. You can see that we have basically the same questions here. So again, if you take a moment to kind of pause and see what you can fill in based on what we did in the last one, then I will have the answers appear. Okay. Just to briefly go over these things. Now our end behavior is switched. It is going to be opposite. So it'll go up on one end and down on the other. If I have a positive leading coefficient, it's up on the right, down on the left. If I have a negative leading coefficient, it's down on the right, up on the left. So you can tell just from looking at a picture, like I said in the first set of examples, because this particular graph goes in opposite directions, one end is up and one end is down, it's definitely going to be an odd degree polynomial. You don't necessarily know the degree, but you know it's an odd degree. And again, because it's up on the left and down on the right, you know that the number in front of the highest powered term is going to be a negative. They all have this sort of x to the third type shape that you can see exhibited here in the first one, but just like with the even degree ones, it's going to flatten more at the middle. These are just for the single term polynomials. But once you add more terms, the same limitation on turning points. In this case, I have 2 turning points. In a 5th degree polynomial, the most it could possibly have would be 4. Domain is still all reals, but in this case, the range is also all reals, because if it's going to go up on one end and down on the other, you're definitely going to hit all the y values in between. Polynomials don't have any breaks, gaps, holes, jumps, or anything like that. All right, so that's a little bit of a review about the graphs. And we're going to do just a couple of examples to kind of get ourselves thinking about these functions. The first one says, find an expression for a cubic function, f, and then it's giving me some values. F of 1 equals 6, f of -1, and f of 0, and f of 2 are all 0. So I'm going to remind you of something, hopefully. Remember that if a x value gives you 0 out of the function, that means it has to be one of these x-intercepts, right? If it's y is 0. It also means something else for the function. Let's see if we can outline this here. Okay. This means that -1, 0, and 2 are roots, solutions, x-intercepts. Those are all different words that mean the same thing. It also means something for the equation. It means that x minus each one of those, so x minus 2, x minus 0, which would just be x, and x minus -1 are all factors of its equation. So remember, like if you're trying to solve an equation and it's written in factored form, you can see that very easily 4 and 3 would be solutions to this equation. So if you know, you can go in reverse. If you know that certain numbers are solutions, then that tells you you can work backwards, that their x minus the number has to be a factor in the equation. It's called the factor theorem. You may not remember it. Hopefully it's ringing a bell. So what we're going to do then, if we're looking for a cubic function, and we know that these 3 things are all factors, then we're going to write our function using those factors. X minus 2, x minus 0 is kind of funky. Can we just write that as x? So if so, I'm going to put it out front. And x plus 1. Okay. So we know these are all factors, and if we multiplied those all out, we would get something cubic. So we're really close to having an answer, but there's got to be a possibility of some coefficient out here as well. So we use the factors we found from the roots, but then we're going to use this one other point, f of 1 equals 6, to help us solve for that a. So if I plug in x equals 1 and y equals 6, x equals 1, y equals 6, that should be a solution to this equation as well, which means I can solve for a. So I have 6 equals Let's see, 1 times -1 times 2, so -2a. So divide by -2. And I get a equals -3. So that gives me a final answer that this function, just plugging in what that a is and leaving my 3 factors. This is an expression for a function that has those 3 roots and that 1 additional point. So actually, the last example we have here is exactly the same thing. It's just that the information is given to you in a graph form instead of in an equation form. It's asking you to find an equation for the polynomial graph here. I'm going to give you a chance to try this. So I'm wanting you to put the video on pause in just a second, but look at those 3 points there. They're all x-intercepts, which means they're all roots, which means something about their factors. And then you're going to need one more point to possibly solve for that a. And I'm thinking that red one there looks like a good choice. So give this a try. Like I said, go ahead and pause the video and see what you can make of it.